So here we're given a fairly simple circuit that we're asked to find the Thevenin equivalent between terminals A and B. So there's A and B, and you can see that they have defined all of the components here, and so they're asking for us to determine what the Thevenin equivalent would be between those terminals. So let's see how we go about this. So the first thing we want to do is determine what the open circuit voltage is. So that's B across A and B. So we're going to just arbitrarily define a couple of nodes here. So the first one that we will define is this one, and we're going to call that VY, which incidentally is also equal to VOC, our open circuit voltage. So if we find VY, we found what we're looking for. And the other node that we see here is right here, and we're going to call that Vx. And so now we should be able to develop some nodal equations and solve for these voltages at these nodes. So let's do that. So we'll solve for the Vx node first. So then as we come across, we will see we have this R1 first, and so the current leaving the node, which we're saying leaving the node is positive, we can write that then as Vx minus V, which we see is 12, and then that's over R1, which we see is 10K. So that's our R1. So moving down the line here, we've got this R2. And so the current from there is just going to be Vx over R2, which again is 10K. And then we see we have this R3 value here. And so we can write the voltage there then, or the current, there. It's going to be Vx minus Vy over R3, which was 5K. And so the only other thing is we have is the independent current source, which is coming into the node. So for convenience, we're going to write that then, that's this source here. We're going to write that then as equal to that current source, which was 1.8 times, well, we'll just say milliamps. We'll take care of that. So milliamps. So it's times 10 to the minus 3. So this is the equation for the currents going in and out of Vx. So then we can come back here and do for Vy. And when we do that, we see we already have the R3 term, so let's do that one. So that's going to be Vy in purple minus Vx, and that's going to be over R3, which was 5K. And then the really only other one we have there is going to be this R4 value. And so we can write that one then as Vy over R4, which is 10K. And that's the only things going in and out of that node. So we can set that one just equal to 0. So now we can simplify these equations a bit. And when we do, what we come up with then is Vx times 4 times 10 to the minus 4 minus Vy times 2 times 10 to the minus 4. And then this is going to equal to 30 times 10 to the minus 4. And then likewise, we can take the second equation. That's going to be minus Vx times 2 times 10 to the minus 4 plus Vy times 3 times 10 to the minus 4. And then that's all equal to 0. So here now we have our two equations and our two unknowns. And so when we solve that, you can do it a number of different ways. You can use linear algebra. You can use variable reduction. Several different types of ways. But the bottom line is, however you solve it, when you get through with it, you should get Vx is equal to 11.25 volts, which we don't really care about that one. What we do care about is this Vy, which we said is equal to our open circuit voltage, which is going to be 7.5 volts. So here's the one we're really interested in. So that's our open circuit voltage. So now we need to determine what our Thevenin resistance is. So to do that, let's reset our circuit here. And so what we're really looking for then is our R Thevenin, and that's looking back into the circuit here. And so remember, when we do that, we open circuit the current sources. So this current source here would be as if it's not even there. So we will just take it out. And then we short circuit our voltage sources. So we'll take this out and then replace that with a short circuit. Okay, and so now looking at this, we can start to reduce things a bit. And so let's write in the values just to make things maybe a little simpler. So we know this is 10K, we know this is 10K, we know that R3 is 5K, and we know that this is 10K. So now if we look at this, the first thing we see is these two guys here, and they are in parallel. And so anytime you have two of the same value in parallel, you can replace it with one resistor of half the value. So we can do that pretty quickly. So let's do that. So then that's going to be, all of this is gone. Sorry about that. And yeah, this is still gone. And so this will now be 5K. Remember, two 10Ks in parallel will give us a 5K in its place. And so now we have these two resistors here in series. So 5K and 5K, that'd be the same as just replacing with a 10K. Right, 5 and 5 is 10 when they're in series. So let's do that. So it's like this one's not here. We'll just short it out like this. And then this guy here now be a 10K. So again, now we see that we have this 10K and this 10K in parallel, and those are the last two that we have. So 10K in parallel with 10K again is just going to be a 5K resistor. All right, so then we can say in summary that our R Thevenin is going to reduce down to 10K in parallel with 10K, and that's going to equal to 5K. So that's our Thevenin resistance. So now we have our open circuit voltage, we have our Thevenin resistance. So now we should be able to draw our Thevenin equivalent circuit. So when we do, remember, Thevenin equivalent circuit is our open circuit voltage here. So that's 7.5 volts. And then that's in series with the Thevenin resistance, which we just determined was 5K ohms. And again, this is A and B. So this is our Thevenin equivalent circuit for our original circuit, which I can reset here for that guy.